So we're going to look at Chapter 2, an overview of chemical connection to biology. Living organisms in the world they live in are subject to the basic laws of physics and chemistry. Biology is a multidisciplinary science drawing on insights from other sciences. Life can be organized into a hierarchy of structural levels. Atoms are organized into molecules, and molecules are organized into cells. At each successive level, additional emergent properties appear. Somewhere in the transition from molecules to cells, we cross the boundaries between non-life and life. One example is the use of formic acid by ants to maintain Devil's Gardens stands of Doria trees. This picture was taken from the Amazon rainforest in South America. As you can see, a small flowering tree called Doria hystricata is all over the place, all right down through here. To the untrained eye, it was thought that local people planted and maintained this area. Come to find out, people had nothing to do with it. Rather, it was all thanks to ants. No, ants did not physically plant Doria tree seeds. Rather, they prevented other plants' growth by injecting formic acid into the plants. These ants lived in the hollows of the Doria trees. By injecting other plants, this allowed for the growth of their home, the Doria trees. Matter consists of chemical elements in pure form and in combinations called compounds. Organisms are composed of matter, defined as anything that has mass and takes up space. Matter is made up of elements. An element is a substance that cannot be broken down into other substances by chemical reactions. There are 92 naturally occurring elements. Each element has a unique symbol, usually the first one or two letters of its name. Some symbols are derived from Latin or German names. A compound is a substance that consists of two or more elements in a fixed ratio. Table salt, for an example, also known as sodium chloride, or NaCl, is a compound with an equal number of atoms of elements of chlorine and sodium. Although pure sodium is a metal, as seen on the left, and chlorine is actually a poisonous gas right there in the middle, they combine to form an edible compound, like we see, table salt. This change in characteristics when elements combine to form a compound is an example of an emergent property. About 20 to 25% of the 92 naturally occurring elements are essential elements that are necessary for living things. There are some variations. Humans have 25 essential elements, while plants only have 17. 4 elements, oxygen, carbon, hydrogen, and nitrogen, make up nearly 96% of living matter. Most of the remaining 4% of an organism's weight consists of calcium, phosphorus, potassium, and sulfur. Trace elements are required by an organism, but only in minute quantities. Some trace elements, like iron, are required by all organisms. Other trace elements are required by only some species. For example, vertebrates require the element iodine for normal activity of the thyroid gland. A daily intake of only 0.15 milligrams of iodine is adequate for normal activity of the human thyroid. Here you just see table 2.1 that has the 4 main elements of the human body along with 7 trace elements. Some naturally occurring elements, such as arsenic, are toxic to most organisms. Some species have become adapted to environments containing toxic elements. For example, some species have been able to adapt to environments containing elements that are traditionally toxic. Serpentine is a jade-like mineral that contains toxic elements like chromium, nickel, and cobalt. Here we have an example of adapting over generations to these conditions. Here we have plants that are growing in a serpentine plant community, and this is a Terbian marsupa lily, also located in a serpentine plant community. Each element consists of unique atoms. An atom is the smallest unit of matter that still retains its properties of an element. Atoms are composed of even smaller parts called subatomic particles. 2 subatomic particles, neutrons and protons, are packed together to form a dense core, the atomic nucleus, at the center of the atom. Electrons can be visualized as forming a cloud of negative charge around the nucleus. Each electron has 1 unit of negative charge, and each proton has 1 positive unit of charge. And neutrons are, well, electrically neutral. The attraction between the positive charges in the nucleus and the negative charges of the electrons keep the electrons in the vicinity of the nucleus. A neutron and a proton have almost identical mass, about 1.7 times 10 to the negative 24th gram per particle. For convenience, a smaller unit, the Dalton, is used to measure the masses of subatomic particles, atoms, and molecules. The mass of a neutron or a proton is close to 1 Dalton. Here we have a picture just to give you a visualization. We have the nucleus in here, and then we're going to discuss the shells, which you often see around the outside, or also known as the cloud of negative charge. That kind of just looks, well, like a cloud. The mass of an electron is about 1/2000th the mass of a neutron or proton. We typically ignore the contribution of the electron when determining the total mass of an atom. All atoms of a particular element have the same number of protons in their nuclei. This number of protons is the element's unique atomic number. The atomic number is written in a subscript before the symbol of the element. For example, subscript 2He means that the atom of helium has 2 protons in its nucleus. Unless otherwise indicated, the atoms have equal number of protons and neutrons and therefore no net charge. Therefore, an atomic number tells us the number of protons and the number of electrons in a neutral atom of a specific element. The mass number is the number of protons and the number of neutrons in the nucleus of the atom. We can determine the number of neutrons in the atom by subtracting the number of protons from the mass number. The mass number is written in a superscript before the element symbol. For example, you would just take a little superscript 4 and then put the symbol for helium, He. Because neutrons and protons each have a mass very close to 1 Dalton, the mass number is an approximation of the total mass of the atom is called the atomic mass. 2 items of the same element that differ in the number of neutrons are called isotopes. In nature, an element occurs as a mixture of isotopes. For example, 99% of carbon atoms have 6 neutrons. Most of the remaining 1% of carbon atoms have 7 neutrons, while the rarest carbon isotope with 8 neutrons. Most isotopes are stable, but they do not tend to lose particles. Both the 6-neutron carbon and the 7-neutron carbon are stable isotopes. The nuclei of some isotopes are unstable and decay spontaneously, emitting particles and energy. 8-neutron carbon is one of these unstable isotopes, or also known as radioactive isotopes. When the 8-neutron carbon decays, one of its neutrons is converted to a proton and electron in a process that carbon is converted to nitrogen, a different element. Radioactive isotopes have many applications in biological research. Radioactive decay rates can be used to date fossils. Radioactive isotopes can also be used to trace atoms through metabolic processes. Radioactive isotopes are also used to diagnose medical disorders. A known quantity of a substance labeled with a radioactive isotope can be injected into the blood, and its rate of excretion in the urine can be measured. Radioactive tracers can be used with imaging instruments such as PET scanners to monitor the body's chemical processes, such as those involved in cancerous growths. Though useful in research and medicine, the energy emitted in radioactive decay is hazardous to life. This energy can damage molecules within living cells. The severity of damage depends on the type and amount of radiation that the organism absorbs. Simplified models of an atom greatly distort the atom's relative dimensions. In an accurate representation of a relative proportion of an atom, if an atom of helium were the size of Yankee Stadium, the nucleus would only be the size of a pencil eraser in the center of the field. The electrons would be like 2 gnats buzzing around the stadium. Atoms are almost mostly empty space. When 2 elements interact during a chemical reaction, it is actually their electrons that are involved. The nuclei do not come close enough to interact. The electrons of an atom vary in the amount of energy they possess. Energy is the ability to cause change by doing work. Potential energy is the energy that matter stores because of its structure or location. Water stored behind a dam has potential energy due to its altitude. That potential energy can be used to do work turning electric generators. Because potential energy has been expanded, the water stores less energy at the bottom of the dam than it did in the reservoir. Electrons have potential energy because their positions are relative to the nucleus. The negatively charged electrons are attracted to the positively charged nucleus. The further electrons are from the nucleus, the more potential energy they have. Changes in the electron's potential energy can occur only in steps of a fixed amount, moving electrons to a fixed location relative to the nucleus. An electron cannot exist between these fixed locations. The different states of potential energy of an electron of an atom are called electron shells. The first shell, closest to the nucleus, has the lowest potential energy. Electrons in the outer shell have higher potential energy. Electrons can change their position only if absorbed or released a quantity of electrons that matches the difference of potential energy between the two levels. So here we have how energy can move from one shell to another only if the energy gains or loses exactly equal to the difference in the energy between the energy levels of the two shells. The first shell, down here, is the closest to the nucleus and have the lowest potential energy. The second shell has more energy, and the electrons in the third shell have even more energy. When energy is absorbed, electrons move further away. When energy loses, electrons move closer to the nucleus. The chemical behavior of an atom is determined by its electron configuration, or the distribution of electrons in the electron shell. The periodic table of elements shows the electron distribution for each element. An abbreviated periodic table of elements shows the distribution of electrons in the first 18 elements from hydrogen to argon. The elements arrange in 3 rows or periods corresponding to the number of valence shells in their atoms. Elements in the same row have the same shells filled with electrons. As we move from left to right in the table, each element has one more electron and proton than the element before. The chemical behavior of an atom depends mostly on the number of electrons in its outermost shell, the valence shell. Electrons in the valence shell are known as valence electrons. Lithium has 1 valence electron, neon has 8. Atoms have the same number of valence electrons, have similar chemical behaviors. An atom with a completed valence shell like neon are inert or chemically non-reactive. All other atoms are chemically reactive because they have incomplete valence shells. The path of electrons are often portrayed in concentric paths, like planets orbiting the sun. In reality, an electron occupies a more complex three-dimensional shape called an orbital. The orbital is the space in which electrons are found about 90% of the time. Each orbital can hold a maximum of 2 electrons. The first shell has room for a single spherical or 1s orbital for its pair of electrons. The second shell can pack a pair of electrons into 1 spherical, s2, orbital and 3 dumbbell-shaped 2p orbitals. The reactivity of atoms arises from the presence of unpaired electrons in one or more orbitals of their valence shells. Electrons occupy separate orbitals within valence shells until forced to share orbitals. The 4 valence shells of carbon each occupy separate orbitals, but the 5th valence electron of nitrogen are distributed into 3 unshared orbitals and 1 shared orbital. When atoms interact to complete their valence shells, it is the unpaired electrons that are involved. The first electron shell can only hold 2 electrons. Here is helium with the first shell filled. Atoms with 2 or more electrons must have the extra electron in higher shells. Lithium has 3 electrons, 2 in the first, 1 in the second. The second shell can hold up to 8 electrons. Neon, with a total of 10, has 2 in the first, 8 in the second, thus filling both shells.